Okay, so this is going to be the first video for the particle physics topic. It's the topic I enjoyed most during the A-level, and it's not particularly maths heavy, and the maths that you do come across is fairly straightforward if you understand the key physical concepts behind it. And in this first video, I'm going to cover the atom and its constituent parts, so what makes up the atom. This should mainly be a recap of GCSE, just with a few additional things you now need to know whilst doing the A-level. So here we've got a diagram of an atom and we're going to label it. The atom has two main parts. First off, we have the nucleus here, which is the central region of the atom. The nucleus itself is composed of two particles. We have neutrons, which I've represented by these black particles. You'll often see neutrons represented in a shorthand by the letter N, and neutrons have no charge. And you can remember this by neutrons coming from the word neutral, and so they have no charge. The second particle in the nucleus are protons, which are represented by these red dots. And protons, similar to neutrons, are represented by the letter P. And protons have a positive charge. What this means is that the nucleus will overall have a positive charge, since it's made up of particles which have a positive charge and also particles which have no charge. A definition we learn during A-level is that of a nucleon, which is just referring to a proton or neutron in the nucleus. And so all of these particles here can be referred to as nucleons. This is important later when we look at something called nucleon number, which is just the total number of nucleons. And so in this case, there are 4 protons and 4 neutrons. And so the nucleon number of this atom would be 8. The second part of the atom we're looking at are these shells of electrons which surround this central region. And so these are what I've represented the electrons as. And you'll often see the shorthand is E minus. And electrons have a negative charge. And as we know, opposites attract. And so it's this electrostatic attraction between the nucleus and electrons, which essentially hold the atom together. Something you may not have thought of are the fact that the protons are so close together in the nucleus, and they all obviously have the same charge, and we know that like charges repel. So for them to be in this configuration, there must be another force involved, and we'll talk about that later. Something I want to talk about are the problems with this diagram, and it's really just a representation of an atom, and that's something to bear in mind always, and it can be quite misleading at times. So the first thing to note is that it's not at all to scale. So if we look at the diameter of the atom, so like the total distance across, it's roughly on the order 10 to the minus 10 meters, which is also called an angstrom, which you don't need to know. Whereas the nucleus of the atom, so from here to here, will be only a few femtometers across. And as we know, 1 femtometer is equal to 10 to the minus 15 meters. So from this we can see the atom is 10 to 100,000 times larger than the nucleus itself, and from this we conclude that the atom is almost entirely empty space, just something to remember. Another problem with this model are the circular shells of electrons, which essentially make the electrons look like planets orbiting the nucleus, which would be like the sun. And this is actually called the Bohr model of the atom. It's named after Niels Bohr, who invented it. It's trying to get at the idea that electrons only exist in discrete energy levels in the atom, and this is represented by them being at certain distances away from the center. Well, this is wrong, but good enough for A-level. You really need to study quantum mechanics at university to get a better appreciation of what the atom actually looks like. The remaining key points I want to cover are that protons and electrons have an equal but opposite charge. So protons are positively charged, electrons are negatively charged, and also the number of protons in an atom will equal the number of electrons. And what this means is these charges cancel out, and so the atom has no overall charge. The number of protons determines the element, and you'll see in the periodic table that the elements are ordered by proton number. So hydrogen are atoms with 1 proton, and helium has 2 protons, etc., etc. This has 4 protons, and so is beryllium, and you'll often refer to it as beryllium-8 because of the nucleon number of 8. Another point is that protons and neutrons are much more massive than the electrons, and so what you can determine from that is that the mass of the atom is concentrated in the central region, so it's concentrated in the nucleus. Next, we're going to look at the table of properties of protons, neutrons, and electrons, and these values will be given in the formula booklet / data sheet, and so there's no need to memorize them, but hopefully you'll be able to recall some of them at least from memory after repeatedly using them. First of all, we're going to look at the mass. You can notice here we are talking about rest mass. At A-level we learned the definition of rest mass as being the mass of a particle when it's stationary. This is actually a special relativity phenomena, which you don't need to know about, that the mass of a particle will actually increase relative to how fast it's moving. This rest mass is given in kilograms, which is the SI unit for mass, SI being a French abbreviation, which translates to the International Standard Units. The rest mass is also given in atomic mass units, and 1 atomic mass unit is defined as 1/12 of the mass of 1 atom of carbon-12, and it's sometimes convenient to use a smaller unit of mass because these particles are very small, and as you can see, the value of their rest mass in kilograms is incredibly small. From this data, we can see protons and neutrons have a similar mass and are roughly 1,800 times more massive than an electron. Be wary of talking about mass and saying the word way, since this is actually incorrect. The way to say it is that protons are much more massive. The data for charge is also given, and so we can see that the neutron has 0 charge, whereas the proton and electron are equally but oppositely charged, with the electron being negatively charged and the proton being positively charged. The SI unit for charge is the coulomb, and this is represented by a capital C. In your formula booklet, you'll be given the magnitude of charge of an electron as 1.60 times 10 to the minus 19 coulombs, and something to take note is that this is positive, a positive value, because it's talking about the magnitude of charge of an electron, so it will be positive. What you need to remember is that an electron, in actual fact, will be the negative of this value in charge. Finally, I'm going to talk about ions, which are formed when atoms lose or gain electrons, and this essentially means there'll be an imbalance in the number of protons and electrons in an ion, and so an ion will have an overall charge, whether it be positive or negative, so will be deflected in an electric field. The thought process behind whether an ion is positively or negatively charged is that if an atom were to lose electrons, it would lose negative charge and hence become a positive ion, whereas the opposite, where an atom were to gain electrons, it would then gain negative charge, and so it would become a negative ion. And so, for example, if an atom were to lose 2 electrons, it would form a positive ion with an overall charge of 3.20 times 10 to the minus 19 coulombs, which is just 2 times 1.60 times 10 to the minus 19 coulombs. So that's all I've got for this video, and hopefully that's been helpful.